Tonight, we embark on a journey spanning billions of kilometers across the cold darkness of the outer solar system, a voyage that will carry us far from the familiar warmth of the sun to a realm of ice and mystery. We travel to a world of unimaginable beauty, a gas giant adorned with rings so magnificent they have captivated human imagination for centuries and inspired countless dreams of what might lie in the depth of space. We travel to Saturn, the jewel of our solar system, and we follow in the path of one of the most ambitious, successful, and transformative space missions ever launched by humankind. This is the story of Cassini, the spacecraft that spent nearly 2 decades exploring the ringed planet and its remarkable family of moons, and in doing so fundamentally transformed everything we understood about our solar system, the possibilities for life beyond Earth, and our very place in the cosmos. The story we will explore tonight spans centuries of human curiosity and decades of technological achievement. It encompasses the observations of astronomers working with primitive telescopes in the 17th century, the dream of spacecraft designers in the 20th century, and the tireless dedication of scientists and engineers who worked for decades to bring that dream to reality. It includes moments of high drama as a spacecraft plunged through the atmosphere of an alien moon and touched down on a world a billion kilometers from home. Moments of discovery as geysers erupted from an icy moon, thought to be geologically dead, and moments of wonder as images revealed landscapes and structures that no human eye had ever seen before. Before we begin this odyssey through the Saturnian system, if you find yourself transported by these deep explorations of space and science, a like or subscribe would help this channel continue bringing you these journeys into the unknown. Now let us travel back through time to understand how humanity first came to know this distant world, and how we eventually sent our robotic emissary to study it in ways our ancestors could never have imagined. Part 1. The Dream of Saturn Through Human History. Close your eyes for a moment and imagine yourself standing in the Mesopotamian desert. Some 3,000 years ago, the air is still and warm, the day's heat slowly releasing. Back into the infinite darkness above, there are no city lights to compete with the heavens, no airplanes crossing overhead, nothing between you and the stars but the thin atmosphere of Earth itself. You look up, and the sky blazes with thousands of points of light, more than any modern city dweller has ever seen. Among them, 5 wandering stars move slowly against the fixed backdrop of constellations, and the most distant of these, the slowest and most deliberate in its celestial journey, is a golden point of light that we know today as Saturn. For as long as humans have gazed upon the night sky, Saturn has held a special place among the wandering stars. To the ancient Babylonians, who tracked celestial movements with meticulous care over 3,000 years ago, Saturn was the most distant planet visible to the naked eye, moving so slowly against the background stars that it took nearly 30 Earth years to complete a single orbit around the Sun. They named it after Ninurta, their god of agriculture, for Saturn's languid movement through the heavens seemed to mark the slow turning of seasons across generations. The ancient Greeks called it Phaenon, meaning the shining one, while the Romans gave it the name we use today, Saturn, after their god of agriculture, wealth, and time itself. There was something fitting about associating this remote world with the god of time, For Saturn's orbital period meant that a human might only witness it, completing one or perhaps two circuits of the sky in an entire lifetime. Throughout antiquity and the medieval period, Saturn remained nothing more than a bright yellowish point of light, the most distant landmark in the known universe. Astrologers attributed to it influences of melancholy and contemplation, fitting for a world so far removed from the warmth of the sun. But in 1610, something remarkable happened that would begin to reveal Saturn's true nature. An Italian mathematician and astronomer named Galileo Galilei turned his newly constructed telescope toward the heavens and pointed it at Saturn. What he saw puzzled him greatly. Saturn did not appear as a simple point of light, nor as a disk like the Moon or Jupiter. Instead, Galileo saw what he described as a planet with ears, or perhaps handles, a central body flanked by two smaller companions that seemed attached to it. His telescope lacked the resolving power to show him the truth, and for years astronomers debated what these mysterious appendages might be. The solution to the puzzle came in 1655 from the Dutch mathematician and astronomer Christian Huygens. Using a more powerful telescope of his own design, Huygens observed Saturn over many nights and finally discerned the truth. Saturn was surrounded by a thin, flat ring inclined to the plane of its orbit, which explained why its appearance changed over time as Earth's viewing angle shifted. In that same momentous year, Huygens also discovered a large moon orbiting Saturn, which he simply called Saturni Luna, the moon of Saturn. We know it today as Titan, the second largest moon in the entire solar system, and a world that would become one of the most fascinating targets for Cassini's exploration over 3 centuries later. The next great figure in Saturn's history was Giovanni Domenico Cassini, an Italian-born astronomer who became the first director of the Paris Observatory. Between 1671 and 1684, Cassini discovered 4 more moons of Saturn. Iapetus, with its mysterious two-toned appearance of one dark and one bright hemisphere, Rhea, Dione, and Tethys. But Cassini's most famous observation came in 1675 when he identified a dark gap in Saturn's ring system. This Cassini division, as it came to be known, demonstrated that the rings were not a single solid structure, but rather composed of multiple distinct components. Cassini correctly surmised that the rings might be made of countless small particles, though this would not be confirmed for many years. Together, Huygens and Cassini laid the foundations of our understanding of the Saturnian system, and it was entirely fitting that the mission sent to explore it in detail would bear both their names. The centuries that followed brought incremental advances in our knowledge. William Herschel discovered 2 more moons, Mimas and Enceladus, in 1789. The following century brought the discoveries of Hyperion in 1848 and Phoebe in 1899. Spectroscopic observations in the early 20th century revealed that Titan possessed a thick atmosphere, the only moon in the solar system known to have a substantial gaseous envelope. By the middle of the 20th century, astronomers had identified the major components of Saturn's ring system, designated the A, B, and C rings from outside to inside, and had begun to understand something of the planet's composition as a world dominated by hydrogen and helium, a smaller cousin to mighty Jupiter. The space age brought our first close encounters with Saturn. NASA's Pioneer 11 spacecraft flew past the ringed planet in September 1979, providing the first up-close images and measurements. Then came the Voyager missions, perhaps the most successful planetary exploration program in history. Voyager 1 arrived at Saturn in November 1980, followed by Voyager 2 in August 1981. These twin spacecraft revolutionized our understanding of the Saturnian system. They revealed Saturn's rings to be far more complex than anyone had imagined, filled with intricate structures, including spokes, kinks, and braided ringlets. They discovered new moons and provided the first detailed images of the major satellites. Voyager 1 made a close flyby of Titan, confirming its thick nitrogen-methane atmosphere, but finding its surface completely hidden beneath an impenetrable orange haze. The spacecraft's cameras could see nothing but a featureless orange ball, tantalizing scientists with mysteries about what might lie beneath. The Voyager missions also discovered something extraordinary at Saturn's North Pole that would puzzle scientists for decades. Hidden within the swirling clouds was a persistent hexagonal pattern, a six-sided jet stream roughly 30,000 kilometers across, with each side longer than Earth's diameter. Nothing like it had ever been seen on any other planet. The hexagon rotates with a period matching Saturn's internal rotation, about 10 hours and 39 minutes, maintaining its shape year after year, despite the turbulent weather systems that rage around it. Scientists speculated about what could create and maintain such a geometric pattern in a dynamic atmosphere, but definitive answers would have to wait for a spacecraft that could study it over time. The Voyager flybys also revealed new moons, bringing Saturn's tally to 17 known satellites. They discovered the narrow F-ring, braided and kinked in ways that suggested complex interactions with nearby moonlets. They found shepherd moons, tiny satellites that gravitationally confine ring material and prevent it from spreading. They imaged the bizarre surface of Iapetus with its dark leading hemisphere and bright trailing side, and the heavily cratered terrain of Rhea, Dione, and Tethys. Each discovery raised new questions, and each tantalizing glimpse demanded deeper investigation. But the Voyager flybys, remarkable as they were, lasted only hours. The spacecraft swept through the system, collected their data, and continued on their journey to the outer planets and eventually interstellar space. The combined time that Voyager 1 and Voyager 2 spent within the Saturn system amounted to less than 2 days. What was needed was a mission that would stay. A spacecraft that could orbit Saturn and study it over years, watching how things changed with the seasons, visiting its moons again and again, making repeated close approaches to probe their secrets. Scientists needed a spacecraft that could circle Saturn not once, but hundreds of times, providing the sustained attention that this magnificent system deserved. The scientific community understood that such a mission would require unprecedented capabilities. It would need to carry a sophisticated suite of instruments to study every aspect of the Saturnian environment: the planet's atmosphere and interior, its magnetic field and radiation belts, its intricate ring system, and its diverse family of moons. It would need enough fuel to perform hundreds of orbital maneuvers over many years, and ideally, it would carry a probe that could descend through Titan's opaque atmosphere and finally reveal what lay beneath those orange clouds that had so frustrated the Voyager cameras. That mission would become Cassini-Huygens, named in honor of the two astronomers who had contributed so much to humanity's understanding of Saturn: Giovanni Cassini, who discovered 4 moons and the great division in the rings that bears his name; Christian Huygens, who first recognized the true nature of the rings and discovered Titan; the mysterious moon that would become one of the mission's primary targets. These pioneers of 17th century astronomy could never have imagined that their names would one day be attached to a robotic explorer traveling billions of kilometers to investigate the world they had studied through primitive telescopes. Yet their careful observations and brilliant deductions laid the foundations upon which modern planetary science was built, and it was fitting that the mission to complete their work would honor their memory. Part 2. The birth of an international mission. The dream of sending an orbiter to Saturn and a probe to explore Titan's mysterious surface began to take concrete form in the 1980s. Scientists on both sides of the Atlantic recognized that a flagship mission to the outer solar system would require international collaboration on an unprecedented scale. The distances involved, the complexity of the science objectives, and the sheer cost of such an undertaking meant that no single space agency could accomplish it alone. In 1982, a joint working group between NASA and the European Space Agency began studying concepts for a Saturn orbiter and Titan probe mission. The collaboration that emerged represented a remarkable partnership between three space agencies spanning two continents. NASA would provide the main spacecraft, the orbiter that would tour the Saturnian system for years. ESA would contribute the Huygens probe, designed to descend through Titan's atmosphere and land on its surface. The Italian Space Agency, Agenzia Spaziale Italiana, or ASE, would provide crucial components, including the spacecraft's high-gain antenna and portions of the radar system that would be essential for penetrating Titan's opaque haze. Late in 1988, ESA formally selected Cassini-Huygens as its next major mission. The following year brought major funding approval in the United States, and the collaboration was cemented. The spacecraft that emerged from this international effort was a marvel of engineering, one of the largest and most sophisticated deep space probes ever built. The Cassini orbiter measured 6.7 meters tall and 4 meters wide, roughly the size of a school bus. Fully fueled, and with the Huygens probe attached, it weighed 5.6 metric tons, making it one of the heaviest interplanetary spacecraft ever launched. Its massive high-gain antenna, 4 meters in diameter, and provided by the Italian Space Agency, would serve both as the primary communication link with Earth and as a shield against ring particle impacts during certain orbital maneuvers. The orbiter carried 12 scientific instruments designed to study virtually every aspect of the Saturnian system. The imaging science subsystem consisted of 2 cameras, a narrow-angle camera for high-resolution imaging and a wide-angle camera for context and atmospheric monitoring. These cameras would eventually return more than 450,000 images, including some of the most iconic photographs in the history of space exploration. The visual and infrared mapping spectrometer could see in wavelengths from ultraviolet through visible to infrared, allowing it to determine the composition of surfaces and atmospheres across the Saturn system. The composite infrared spectrometer measured thermal emission, providing temperature maps and compositional data for Saturn, its rings, and its moons. The radar system, one of Cassini's most crucial instruments for studying Titan, operated in multiple modes. It could function as a synthetic aperture radar, creating detailed images of Titan's surface. Through the opaque haze, it could work as an altimeter, precisely measuring surface heights. and it could operate as a radiometer, sensing thermal emission from surfaces. This versatile instrument would eventually map much of Titan's surface, revealing features that had been completely unknown before Cassini's arrival. Cassini's magnetometer extended on a boom 11 meters from the spacecraft body, positioning it away from the electromagnetic interference created by the vehicle's electronics. This instrument would measure the strength and direction of magnetic fields throughout the Saturnian system, mapping Saturn's magnetosphere and detecting interactions with the solar wind, the rings, and the moons. The radio and plasma wave science instrument, with its 10-meter antennas, would detect radio emissions from Saturn and plasma waves in the magnetosphere, including the lightning-generated radio bursts from storms in the planet's atmosphere. Other instruments included the cosmic dust analyzer, which would capture and analyze tiny particles throughout the Saturn system, determining their composition and velocity. The ion and neutral mass spectrometer, which would sample gases and ions directly, sniffing the tenuous atmospheres of moons and the material in the rings, and the magnetospheric imaging instrument, which would create images of Saturn's magnetosphere, visualizing the invisible structures of charged particles that surround the planet. The Huygens probe, nestled against the side of the orbiter, was itself a remarkable piece of engineering. Weighing 349 kilograms and measuring 2.7 meters across, it was designed to survive the most challenging atmospheric entry ever attempted. Titan's atmosphere, though thicker than Earth's, presented unique challenges. The probe would need to withstand tremendous heating during entry, then slow down using parachutes in an atmosphere of unknown density, all while operating in temperatures approaching minus 180 degrees Celsius. Huygens carried 6 instruments to study Titan's atmosphere and surface during its descent, including cameras, spectrometers, and sensors to measure temperature, pressure, and wind. One of the most controversial aspects of the mission was its power source. At Saturn's distance from the Sun, roughly 10 times farther than Earth, solar panels would need to be impossibly large to generate sufficient electricity. Instead, Cassini would draw its power from radioisotope thermoelectric generators, devices that convert heat from the decay of plutonium-238 into electricity. The spacecraft carried 33 kilograms of plutonium dioxide, the largest amount of radioactive material ever launched into space. This decision sparked significant public opposition. Citizen groups concerned about the environmental risks of a launch failure filed lawsuits attempting to halt the mission. Protesters gathered outside the Kennedy Space Center, and the controversy made headlines around the world. NASA and the mission team worked to address these concerns, conducting extensive safety analyses that showed the risk of plutonium release was extremely small, and that even in a worst-case scenario, the impact on human health would be minimal. The plutonium was encased in multiple layers of protective material designed to survive even the most catastrophic launch failure. After careful review, the mission was cleared to proceed. In retrospect, the decision proved wise, as the radioisotope generators performed flawlessly throughout the mission, providing reliable power for nearly 20 years. The development of Cassini-Huygens spanned more than a decade and faced numerous challenges beyond the plutonium controversy. Congressional budget pressures in the early 1990s repeatedly threatened to cancel the mission. In both 1992 and 1994, Cassini came under serious political fire, with some legislators questioning whether such an expensive mission was justified. NASA successfully argued that cancellation after ESA had already invested heavily in the project would damage international relations and make future collaborations more difficult. The mission survived, though its budget was trimmed and some instruments were scaled back or eliminated. At its peak, the Cassini-Huygens team involved more than 5,000 engineers, scientists, and other personnel from 17 countries. The total cost of the mission, including development, launch, and operations through its planned 11-year primary mission, came to approximately $3.26 billion, with NASA contributing about 80%, ESA about 15%, and ASI about 5%. It was an enormous investment, but one that would pay scientific dividends far exceeding what anyone could have predicted when those first planning studies began in the early 1980s. Part 3. The 7-year journey to Saturn. In the pre-dawn darkness of October 15, 1997, at Launch Complex 40 of Cape Canaveral Air Force Station in Florida, a Titan 4B rocket stood ready. Mounted atop this powerful launcher, protected within its payload fairing, sat the Cassini orbiter with Huygens attached. At 4:43 in the morning Eastern Time, the rocket's engines ignited, and Cassini-Huygens began its journey to Saturn. The Titan 4B was one of the most powerful rockets in the American fleet, yet even it could not send such a massive spacecraft directly to Saturn. The distance was simply too great, and reaching Saturn would require a far more circuitous route, one that would span nearly 7 years and carry the spacecraft twice past Venus, once past Earth, and once past Jupiter. This complex trajectory made use of gravity assists, a technique that allows spacecraft to gain speed by borrowing energy from planets. As a spacecraft swings close to a planet, the planet's gravity accelerates it, essentially slingshotting it toward its destination at higher speed than it could achieve with rocket power alone. For Cassini, the path to Saturn required 4 such gravity assists. The first came on April 26, 1998, when Cassini flew within 284 kilometers of Venus, gaining about 7 kilometers per second of speed. The spacecraft then looped around the Sun and returned to Venus for a second flyby on June 24, 1999, passing within 600 kilometers of the cloud-shrouded planet. Between the Venus encounters, mission controllers used Cassini's instruments to observe the planets and calibrate its systems. The spacecraft was functioning well, its instruments returning excellent data during these planetary flybys. On August 18, 1999, Cassini swung past Earth at a distance of about 170 kilometers above the eastern South Pacific. For those who had protested the plutonium power source, this was a moment of anxiety, but the flyby proceeded without incident, giving Cassini another boost of speed toward the outer solar system. The final gravity assist came at Jupiter on December 30, 2000. Cassini passed within 10 million kilometers of the giant planet, close enough to capture stunning images and valuable scientific data. For 6 months, as Cassini approached, flew past, and departed Jupiter, it observed the planet and its moons, coordinating with NASA's Galileo spacecraft, which was already in orbit around Jupiter. Cassini's observations of Jupiter provided valuable tests of its instruments and allowed scientists to compare data from the 2 spacecraft. The images Cassini returned of Jupiter's swirling storms, its ghostly auroras, and its retinue of moons offered a preview of the kind of science the spacecraft would conduct at Saturn. The years between Jupiter and Saturn were ones of patient waiting. The spacecraft cruised through the emptiness of the outer solar system, conserving fuel and awaiting its arrival. Periodic instrument checks and trajectory corrections kept everything on track. Inside the Huygens probe, attached to Cassini's side, systems lay dormant, ready to be awakened after the journey's end. The team, Earth monitored the spacecraft's health, planned the complex orbital tour that would unfold at Saturn, and prepared for the discoveries that surely awaited. On May 18, 2004, Cassini captured its first resolved image of Saturn and Titan from a distance of 28.5 million kilometers. The rings were clearly visible, a tantalizing preview of wonders to come. As the weeks passed, the images grew sharper and more detailed. Then came the critical maneuver that would determine the mission's success or failure. On June 30, 2004 Pacific Time, Cassini began its Saturn orbit insertion burn. For 96 minutes, the spacecraft's main engine fired, slowing Cassini just enough to be captured by Saturn's gravity. It was a moment of high tension for the mission team at the Jet Propulsion Laboratory in Pasadena, California. The burn had to be precise, too short, and Cassini would fly past Saturn and continue into the void. Too long, and the spacecraft would crash into the planet or its rings. During the burn, Cassini passed through the gap between Saturn's F and G rings, crossing the ring plane at a location chosen for its relative emptiness. Even so, the spacecraft's thrusters had to fire repeatedly to counter the pressure of ring particles striking its high-gain antenna, which was pointed forward as a shield. The impact of countless tiny ice particles sounded like rain on a roof, recorded by Cassini's radio and plasma wave instrument. Then, as the burn ended and the data came through, the mission team could celebrate. Cassini was in orbit around Saturn. After nearly 7 years and 3.5 billion kilometers of travel, the spacecraft had arrived at its destination. The exploration of the Saturnian system was about to begin in earnest. Part 4. Huygens' historic descent to Titan. For months after arriving at Saturn, the Cassini orbiter made close flybys of several moons while preparing for the mission's next major milestone, the release of the Huygens probe to Titan. The orbiter repeatedly swept past Titan, its radar and infrared instruments peering through the thick haze to map the moon's surface. These observations helped mission planners select a landing site, though in truth, so much remained unknown about Titan that they could only hope for the best. The landing would take Huygens to a region called Xanadu and the bordering dark terrain, an area chosen because it appeared to offer a reasonable chance of solid ground. On Christmas Day 2004, at 02:00 Universal Time, pyrotechnic bolts fired in springs pushed the Huygens probe away from the Cassini orbiter. After more than 7 years attached to its mothership, Huygens was on its own. The probe carried no propulsion system. It was now on a ballistic trajectory that would take it to Titan in 22 days. During this coast phase, Huygens remained dormant, its systems powered down to conserve its limited batteries. 2 onboard timers counted down the seconds until it would need to wake up and face the most challenging atmospheric entry in the history of space exploration. On January 14, 2005, that countdown reached 0. At 09:06 Universal Time, Huygens entered the upper reaches of Titan's atmosphere at a velocity of about 6 kilometers per second. The probe was now 1.2 billion kilometers from Earth, making this the most distant landing ever attempted. No human commands could help now. The round-trip time for radio signals was about 134 minutes, meaning Huygens had to handle everything autonomously based on programs loaded before launch. The descent would be over long before any signal from Earth could reach it. As Huygens plunged into Titan's atmosphere, its heat shield absorbed the tremendous energy of entry, heating to temperatures exceeding 1800 degrees Celsius. The probe decelerated rapidly, experiencing peak forces of about 16 times Earth's gravity. Within minutes, the velocity had dropped from hypersonic to subsonic. At an altitude of about 160 kilometers, the drogue parachute deployed, pulling away the heat shield and exposing Huygens' instruments to Titan's atmosphere for the first time. The main parachute, 8.5 meters in diameter, opened immediately afterward, slowing the probe's descent dramatically. For the next 2 hours and 27 minutes, Huygens drifted down through Titan's atmosphere, its 6 instruments busily collecting data. The gas chromatograph mass spectrometer sniffed the atmosphere, identifying nitrogen as the dominant component, with methane making up about 5% near the surface. The Huygens atmospheric structure instrument measured temperature, pressure, and density at various altitudes. The descent imager spectral radiometer began taking photographs and spectra, revealing a world that looked startlingly Earth-like in many ways. As Huygens descended through the haze layer, images began to show surface features. Scientists watching the data stream back through Cassini's relay could scarcely believe what they were seeing. There were dendritic drainage channels cutting through brighter highlands, looking for all the world like river networks on Earth. Dark plains spread across lower elevations, resembling coastlines and lake beds. Though no liquid was visible in the area where Huygens was landing, the evidence for past or seasonal liquid flow was unmistakable. This was not a dead, cratered world like so many moons in the outer solar system. This was a world with weather, with active geology, with a hydrological cycle remarkably similar to Earth's, except the working fluid was not water, but methane. About 45 minutes into the descent, the main parachute was released, and a smaller drogue deployed. This was necessary because the main parachute would have resulted in a descent lasting many hours, potentially exhausting the batteries before landing. The smaller parachute allowed Huygens to descend more quickly while still providing a soft landing. As the probe dropped below the haze layer, visibility improved dramatically. The camera captured increasingly detailed views of the surface, showing what appeared to be a sandy plain littered with rounded pebbles of water ice. At 12:43 Universal Time, Huygens touched down on the surface of Titan. The impact was gentle, equivalent to dropping from a height of about 1 meter in Earth's gravity. The accelerometers recorded the probe briefly sinking into the surface, penetrating about 15 centimeters before coming to rest. The landing site turned out to be a dry riverbed or lake bed, the surface having the consistency of wet sand mixed with icy pebbles. The surface penetrometer detected warmth being released from beneath the surface as Huygens settled, suggesting that the probe's heat was evaporating some kind of volatile material, likely methane, from the ground. Huygens continued transmitting from the surface for another hour and 12 minutes, far longer than its designers had dared hope. The cameras captured a panoramic view of a remarkably Earth-like landscape, a flat, sandy plain stretching to the horizon. strewn with rounded pebbles and small rocks composed of dirty water ice. The lighting was dim, about 1,000th the brightness of a sunny day on Earth, yet enough to see clearly. The sky above was a hazy orange. It was an alien world, yet one that any human could have stood upon and recognized as a landscape, a place. Back on Earth, the Huygens data created a sensation. Here was another world with rain and rivers, with erosion and deposition, with weather and seasons. The chemistry was exotic, based on hydrocarbons rather than water, but the processes were hauntingly familiar. Scientists realized that Titan offered an unprecedented laboratory for studying organic chemistry in conditions that might resemble the early Earth before life arose. The successful landing, the first in the outer solar system and the most distant from Earth ever achieved, demonstrated what was possible when nations combine their talents and resources in the pursuit of knowledge. Part 5. Titan, an Earth-like world in deep space. While Huygens provided our only direct glimpse of Titan's surface, landing successfully but transmitting for only a few hours before its batteries were exhausted, the Cassini orbiter would continue studying this extraordinary moon for the next 13 years. Each of the 127 close flybys brought new revelations, sometimes passing within just 1,000 kilometers of Titan's surface. Cassini's instruments peeled back more layers of mystery with every encounter. The radar pierced the orange haze to reveal surface features. The infrared instruments mapped atmospheric temperatures and compositions at different altitudes. The cameras captured occasional glimpses of the surface through windows in the haze at certain wavelengths. Piece by piece, flyby by flyby, the picture that emerged was of a world that resembles Earth more closely than any other in our solar system, yet remains utterly alien in its chemistry and conditions. Titan is the second largest moon in the solar system, exceeded in size only by Jupiter's Ganymede. With a diameter of 550 kilometers, it is larger than the planet Mercury and about 40% the diameter of Earth. If it orbited the Sun instead of Saturn, it would qualify as a planet in its own right. It is the only moon in the solar system known to possess a thick atmosphere, one that is even denser than Earth's. At Titan's surface, the atmospheric pressure is about 1.5 times that at sea level on Earth, roughly equivalent to the pressure experienced by a scuba diver at a depth of 5 meters. If you could stand on Titan's surface and had no need to breathe, you would not require a pressure suit, only protection from the cold that would freeze you solid within minutes. The atmosphere is composed primarily of nitrogen, about 95% by volume, remarkably similar to Earth's 78% nitrogen composition. Methane makes up most of the remainder, typically 2 to 5% depending on altitude and location. But it is the trace constituents that make Titan's atmosphere so fascinating. Hydrogen cyanide, ethane, propane, acetylene, diacetylene, methylacetylene, cyanoacetylene, and dozens of other organic molecules created when ultraviolet radiation from the sun breaks apart nitrogen and methane in the upper atmosphere, and the fragments recombine in new configurations. These complex molecules, collectively known as tholins, give Titan its characteristic orange color and create the hazy smog that veils the surface from view. The haze is so thick that standing on Titan's surface, you would never see the sun directly. The sky would be a uniform orange glow, like an overcast day on Earth, but with an alien tint that would mark it instantly as otherworldly. Cassini measured the amount of sunlight reaching the surface and found it to be only about 1% of the sunlight reaching Earth, and most of that is scattered and diffused by the atmosphere. Noon on Titan is about as bright as twilight on Earth, dim enough that you would strain to read a book, but bright enough to see clearly for great distances across the landscape. The Cassini radar, capable of penetrating this haze, revealed that Titan's surface is geologically young and remarkably varied. Near the equator, vast fields of longitudinal dunes stretch across the landscape, their dark material likely composed of organic particles that have rained out of the atmosphere over millions of years. These dunes, remarkably similar in form to sand dunes in Earth's deserts, cover about 20% of Titan's surface. They reach heights of 100 to 150 meters and extend for hundreds of kilometers, shaped by winds in Titan's dense atmosphere. But the most startling discovery came in the polar regions. There, Cassini found liquid lakes and seas, the only stable bodies of surface liquid known anywhere in the solar system besides Earth. The largest of these is Kraken Mare, in the northern hemisphere, covering an area of about 400,000 square kilometers, larger than the Caspian Sea on Earth. Ligaea Mare and Punga Mare are the next largest, together with Kraken Mare, accounting for about 80% of Titan's total liquid coverage. These seas are not filled with water. They are composed of liquid methane and ethane, hydrocarbons that exist as gases on Earth, but are liquid at Titan's frigid surface temperature of about -179 degrees Celsius. The depths of these bodies of liquid were measured by Cassini's radar during close flybys. Ligaea Mare was found to be surprisingly deep, exceeding 160 meters in places, with a bottom covered in organic-rich sediment. The composition turned out to be mostly pure liquid methane, somewhat to scientists' surprise, as they had expected a greater proportion of ethane based on atmospheric models. This discrepancy could indicate complex processes at work, perhaps underground reservoirs feeding the lakes or seasonal. Variations in composition that remain to be fully understood. Titan has an active hydrological cycle, analogous to the water cycle on Earth, but operating with methane instead of water. Methane evaporates from the lakes and seas, rises into the atmosphere, forms clouds, and falls as rain. This rain feeds rivers that carve channels in the icy landscape and carry sediment to the lowlands. The drainage networks, visible in Huygens imagery and mapped by Cassini radar, bear striking resemblance to terrestrial river systems. Near the landing site, the channels appear to have been carved by recent flows, though no liquid was present when Huygens arrived. The region may experience seasonal flooding, with methane rain filling the channels during wetter periods. The weather on Titan unfolds on timescales vastly longer than Earth's seasons. Because Saturn takes nearly 30 years to orbit the Sun, and Titan shares this orbital period as it circles Saturn. A single year on Titan lasts almost 3 Earth decades. Cassini arrived during Saturn's northern winter and observed the progression through equinox in 2009 to northern summer in the mission's final years. Over this span, scientists watched cloud patterns shift from the South Pole to the North Pole, tracking the movement of Titan's weather systems as the seasons slowly changed. Beneath Titan's icy crust, Cassini found evidence for another ocean, this one likely composed of liquid water mixed with ammonia. Measurements of Titan's rotation and gravity revealed that the moon's crust does not move as a rigid body with its interior. Instead, the surface appears to float on a global subsurface ocean, similar to what has been inferred for Jupiter's moon Europa. Based on the gravitational data, this internal ocean lies perhaps 50 to 100 kilometers below the surface, kept liquid by the warmth generated by tidal heating from Saturn's gravity. The presence of liquid water within Titan, combined with the rich organic chemistry on its surface, makes the moon an intriguing target in the search for life, though any organisms would face the challenge of extremely cold temperatures at the surface and deep isolation within the interior. The atmosphere of Titan is a chemical factory of stunning complexity. When ultraviolet light strikes methane molecules high in the atmosphere, it breaks them apart, beginning a cascade of reactions that builds progressively more complex organic molecules. Cassini's instruments detected a veritable zoo of compounds, including hydrogen cyanide, benzene, and even more complex polycyclic aromatic hydrocarbons. These molecules link together to form solid particles that gradually sink through the atmosphere, eventually reaching the surface as a continuous drizzle of organic material. Over billions of years, this process has coated Titan's surface with what scientists have estimated to be hundreds of times more hydrocarbons than all the known oil and natural gas reserves on Earth. This prebiotic chemistry is of particular interest to astrobiologists. On early Earth, before life arose, similar organic compounds likely played a role in the origin of life. Titan offers a natural laboratory where these processes can be studied in an environment free of life, allowing scientists to understand how far chemistry alone can go toward building the molecules needed for biology. While Titan itself is probably too cold for life as we know it, studying its chemistry may help us understand how life might originate on other worlds. Part 6. Enceladus, Ocean World and the Quest for Life. Before Cassini arrived at Saturn, the tiny moon Enceladus was considered something of an afterthought, a small icy body unworthy of special attention. At just 504 kilometers in diameter, about the width of Arizona, Enceladus was far too small to be geologically active by any conventional understanding of planetary science. Small bodies lack the mass to retain internal heat. They cool quickly after formation and become geologically dead, their interiors frozen solid, their surfaces ancient and unchanged except for the slow accumulation of impact craters. Or so scientists thought. Previous spacecraft had noted that Enceladus was exceptionally bright, reflecting nearly 100% of the sunlight that struck it, making it one of the most reflective bodies in the solar system. Only fresh snow or ice could be so white. Any exposed surface in the solar system gradually darkens over time from the accumulation of dust, the bombardment of energetic particles, and the photochemical reactions caused by ultraviolet radiation. The brightness of Enceladus suggested that something was refreshing its surface, coating it with pristine material. But what process could be active on such a small, cold body? The Voyager missions had flown past quickly, revealing a surface that appeared young in some areas, but offering no explanation for the unusual brightness. Enceladus remained a puzzle, a minor mystery among the many wonders of the Saturnian system. There were other hints that something unusual might be happening at Enceladus. Astronomers had long known that Saturn's tenuous E-ring, the diffuse outer ring that extends from the orbit of Mimas past the orbit of Titan, was somehow connected to Enceladus. The ring particles appeared to originate from the vicinity of this moon, but how particles were being injected into space from a supposedly dead world was unclear. Some scientists speculated about cryovolcanism, the eruption of water and ice rather than molten rock, but without direct evidence, this remained speculation. In February 2005, just weeks after the Huygens landing on Titan, Cassini made its first close flyby of Enceladus. The spacecraft's magnetometer detected something strange. Saturn's magnetic field was being distorted near the moon, as if something were pushing against it. A magnetic field can be deflected by an atmosphere, a plasma environment, or material escaping from a body into space. But Enceladus was supposed to be a frozen dead world, far too small and cold to have any atmosphere or outgassing. How could such a tiny body be affecting Saturn's magnetic field? The answer came spectacularly in July 2005, when Cassini flew past Enceladus's south polar region and imaged something that no one had predicted and few had even considered possible. Enormous plumes of icy material were erupting from fissures in the moon's surface, jetting hundreds of kilometers into space in towering fountains of vapor and ice particles. Backlit by the distant sun, these geysers were clearly visible against the blackness of space, dramatic proof that this tiny world was spectacularly, violently alive. The discovery sent shockwaves through the planetary science community. Here was active geology on a world where physics said there should be none. The images were stunning. Multiple jets emanated from the south polar region, some extending more than 500 kilometers above the surface before the material dispersed into space. The particles spread out in a broad plume that could be traced far from the moon. Some of this material fell back to the surface as snow, explaining why Enceladus was so bright and why its surface appeared young. But much of the ejected material escaped the moon's weak gravity and entered orbit around Saturn, where it became part of the E-ring. The mystery of the E-ring was solved. Enceladus was actively feeding it with freshly erupted ice. The fissures from which the plumes erupted became known as the Tiger Stripes, 4 parallel ridges running across Enceladus's south pole. Each tiger stripe is about 100 to 30 kilometers long, 2 kilometers wide, and flanked by ridges about 100 meters high. They were named Alexandria, Baghdad, Cairo, and Damascus, after cities mentioned in the Arabian Nights tales. Infrared observations showed that these fissures were far warmer than their surroundings, with temperatures reaching about -93 degrees Celsius compared to the average surface temperature of -198 degrees Celsius. While -93 degrees is still extremely cold by terrestrial standards, it represented a remarkable heat source for a world that should have been uniformly frozen. Mission planners quickly recognized the significance of this discovery and redesigned Cassini's orbital tour to maximize encounters with Enceladus. Over the following 12 years, the spacecraft would make more than 20 close flybys of the tiny moon, sometimes diving directly through the plumes to sample their contents with its instruments. Each flyby brought new discoveries that transformed Enceladus from an obscure icy satellite into one of the most compelling destinations in the search for life beyond Earth. During a close flyby in 2008, Cassini's instruments sampled the plume directly and detected a surprising mix of volatile gases, water vapor, carbon dioxide, and carbon monoxide, as well as organic materials. The density of organic materials was about 20 times higher than scientists had expected, suggesting a rich source of carbon-based molecules beneath the surface. The plumes are composed almost entirely of water vapor, about 98%, with the remainder consisting of carbon dioxide, methane, ammonia, and simple organic molecules, including propane and ethane. The density of organic material was about 20 times higher than scientists had expected. Crucially, Cassini's instruments detected sodium and potassium salts in the ice grains, in concentrations suggesting that the water was salty, like an ocean. The presence of these salts indicated that the water had been in contact with rock, undergoing chemical reactions that dissolved minerals into solution. Based on this chemistry, scientists concluded this was not condensation from the vacuum of space. This was ocean water from deep within the moon, spraying out through cracks in the ice. Over multiple flybys and years of analysis, scientists assembled a picture of Enceladus's interior. Beneath a global ice shell, perhaps 20 to 25 kilometers thick, the data indicate a liquid water ocean in contact with a rocky core. Tidal heating, generated by the gravitational tugging of Saturn, as Enceladus follows its slightly elliptical orbit, keeps this ocean from freezing. The ocean appears to be global, extending beneath the entire surface, though models suggest it may be thinner at the equator and thicker at the poles. The total volume of liquid water could rival that of Earth's largest seas. More remarkably still, Cassini found evidence that hydrothermal activity occurs at the boundary between the ocean and the rocky core. During a close flyby in October 2015, the spacecraft flew through the plumes and detected significant amounts of molecular hydrogen. Based on what we know about geochemistry, this hydrogen can best be explained as the product of hydrothermal reactions, where hot water circulates through rock, causing chemical changes that release hydrogen gas. On Earth, such hydrothermal vents support thriving ecosystems of microbes and larger organisms, communities that derive their energy not from sunlight, but from the chemical reactions between hot rock and water. If similar vents exist on Enceladus, they could potentially support life. In June 2023, researchers analyzing Cassini data made another breakthrough discovery. Phosphorus had been detected in the ice grains from Enceladus's plumes. Phosphorus is a key element for life as we know it, essential for DNA, RNA, and the energy-carrying molecule ATP. The concentrations detected suggested that Enceladus's ocean contains phosphorus in amounts at least 100 times greater than Earth's oceans. With this discovery, all 6 elements considered essential for life as we know it, carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur, had been detected in material from Enceladus. The moon has water, energy from hydrothermal activity, and the chemical building blocks of life. Whether life has actually arisen, there remains an open and tantalizing question. The discovery of Enceladus's ocean fundamentally changed how scientists think about habitability in the solar system. Before Cassini, the habitable zone was typically defined as the region around a star where liquid water could exist on a planet's surface, not too hot and not too cold. This definition placed only Earth squarely within our Sun's habitable zone, with Mars on the outer edge. But Enceladus demonstrated that liquid water oceans can exist far beyond this zone, kept warm by internal heating rather than stellar radiation. Ocean worlds may be common throughout the galaxy, orbiting not in the traditional habitable zone, but anywhere that tidal or radioactive heating can maintain liquid water beneath an icy shell. The implications extend to the search for life elsewhere in the cosmos. When astronomers look for potentially habitable planets around other stars, they can now consider not just rocky planets in the habitable zone, but also icy moons orbiting gas giants far from their parent stars. The number of potentially habitable worlds in the universe may be vastly larger than previously estimated. Cassini's discovery at Enceladus did not find life, but it showed us new places to look and new ways to think about where life might arise. Part 7. Saturn's Rings. Ancient Mystery, Young Reality. For 4 centuries, Saturn's rings have symbolized the planet's majesty, setting it apart from every other world in our cosmic neighborhood. From Galileo's puzzling first observations through his primitive telescope, which he interpreted as handles or ears attached to the planet, through Huygens' recognition of their true nature as a thin, flat ring, through Cassini's discovery of the great division that now bears his name, the rings have beckoned as objects of transcendent beauty and scientific curiosity. No other feature of our solar system is quite so immediately recognizable, quite so universally associated with wonder and mystery. The Cassini mission spent 13 years studying these magnificent structures from a vantage point no human observer had ever enjoyed, circling within and around them, photographing them in every possible lighting condition, measuring their properties with a dozen instruments, and what it found upended many long-held assumptions about their nature, structure, origin, and age. The main rings span roughly 280,000 kilometers from inner edge to outer, a distance that would stretch nearly 3/4 of the way from Earth to the Moon. Yet despite this enormous breadth, the rings are astonishingly thin, generally less than 10 meters thick, and in some places as thin as a few meters. If the rings were scaled down to the size of a standard sheet of paper, that paper would need to be about 10,000 times thinner than it actually is to maintain the same proportions. Another way to visualize this, if you could somehow drive across the rings in a car at highway speed, crossing their full 280,000 kilometer width would take nearly 4 months of continuous driving. But if you could somehow descend through them at the same speed, you would pass through their thickness in less than a second. Despite this extreme thinness, the rings contain an enormous amount of material, almost entirely water ice, with only small amounts of rocky silicate material and organic compounds mixed in. The particles range in size from microscopic specks smaller than grains of sand to house-sized boulders and even car-sized chunks, with most of the mass concentrated in particles ranging from a few centimeters to a few meters across. If all the ring material could somehow be gathered together and compressed, it would form a solid sphere, perhaps 400 to 600 kilometers in diameter, smaller than Saturn's moon Mamas. Yet spread out in their thin disk, the rings dominate visual observations of the planet. The rings are conventionally divided into several distinct components, lettered in the order of their discovery rather than their position. The brightest and most prominent are the A and B rings, separated by the Cassini division, a dark gap some 4,800 kilometers wide that is easily visible through a small telescope from Earth. The C ring, sometimes called the crepe ring because of its translucent appearance, lies inside the B ring. Beyond the A ring lies the narrow F ring, a thin strand of material shepherded by 2 small moons. Still further out are the G and E rings, much fainter and more diffuse. The D-ring, closest to Saturn, is extremely tenuous and was not discovered until the Voyager missions. Within and between these major components lie hundreds of finer structures, gaps, ringlets, waves, and features that reveal the complex dynamics at work. Cassini revealed the rings to be far more dynamic and intricately structured than any previous observations had suggested. Where earlier spacecraft and ground-based telescopes saw relatively smooth, continuous bands of material, Cassini found structures at every scale from thousands of kilometers down to tens of meters. Some of these features are transient, appearing and disappearing over days or weeks as gravitational forces reshape the ring material. Others are stable, maintained by the same forces that created them billions of orbits ago. Gravitational interactions between ring particles and Saturn's many moons create waves and gaps that propagate through the rings like ripples on a pond. When a moon orbits near the rings, its gravity tugs on nearby ring particles, perturbing their orbits. If the moon's orbital period is a simple fraction of the orbital period of ring particles at a particular location, a resonance occurs, and the cumulative effect of many small tugs can open a gap or create a wave pattern. The Cassini division, for example, is swept clear by a 2.1 resonance with the moon Mimas. Ring particles in the division orbit Saturn exactly twice for every one orbit of Mimas, and the repeated gravitational kicks from Mimas push them out of that region. The F-ring, Saturn's outermost discrete ring, proved to be among the most dynamic features in the entire system. This narrow ribbon of material is shepherded by two small moons, Prometheus and Pandora, whose gravitational tugs create a constantly changing pattern of kinks, braids, and jets. Cassini watched as collisions between the ring and moonlets created ephemeral features that appeared and disappeared over weeks and months. One object, dubbed S2004 S6, may have been created by such a collision during Cassini's observations. At the equinox in August 2009, when the sun shone edge-on to the rings, Cassini observed something remarkable. The low-angle lighting cast shadows from vertical structures in the rings that had previously been invisible. Some of these structures rose as high as 2.5 kilometers above the ring plane, as tall as some of the rocky mountains created by the gravitational influence of embedded moonlets or by impacts that temporarily threw material out of the ring plane. The equinox observations revealed the rings as three-dimensional structures, not the infinitely thin sheets they appear to be from most viewing angles. Perhaps the most significant discovery regarding the rings came during Cassini's final orbits, when the spacecraft dove between the rings and Saturn's cloud tops to measure the mass of the rings with unprecedented precision. By tracking tiny changes in Cassini's velocity caused by the gravitational tug of the rings, scientists could calculate how much material they contain. The answer surprised many researchers. The rings have a mass of about 40% of the moon Mimas, roughly 15 billion kilograms. This is far less than some earlier estimates and carries profound implications for the ring's age. Low mass suggests youth. If the rings were as old as Saturn itself, roughly 4.5 billion years, they would have accumulated far more contaminating material from meteoroid impacts over that time. The bright, pristine ice we see today would have been darkened by this constant rain of debris. Yet the rings are remarkably clean. Combined with the mass measurements, This evidence points toward the rings having formed relatively recently in geological terms, perhaps only 10 to 100 million years ago, during the age of the dinosaurs on Earth. Based on these findings, Saturn may have spent most of its existence without its iconic rings, acquiring them through some catastrophic event. Perhaps a comet struck an icy moon, shattering it into the debris that became the rings, or gravitational interactions could have destroyed a moon that wandered too close to the planet. This finding upended the traditional view that Saturn's rings are primordial, a remnant of the solar system's formation. Instead, the rings appear to be a temporary phenomenon. Cosmically speaking, material is constantly being lost from the rings, spiraling inward onto Saturn due to processes including meteoroid bombardment and electromagnetic interactions. Cassini measured this inflow and found it far more rapid than expected. At current rates, the rings may persist for only another few 100 million years before vanishing entirely. If intelligent beings exist elsewhere in the galaxy and gaze at Saturn tens of millions of years from now, they may see a ringed planet with only faint, tenuous bands, or perhaps no visible rings at all. The rings also served as cosmic seismographs, recording vibrations from deep within Saturn itself. Cassini observed spiral patterns in the C-ring created by oscillations in Saturn's interior, allowing scientists to probe the planet's internal structure in ways previously impossible. These measurements revealed that Saturn's core is not a compact ball of heavy elements, as models had suggested, but rather extends about halfway to the planet's surface and is diffuse, mixed with the surrounding hydrogen and helium. The rings proved to be windows into Saturn's hidden depths. Part 8. The Gas Giant. Storms, Hexagons, and Mysteries. While the moons and rings captured much of the public's attention, Cassini also transformed our understanding of Saturn itself, the massive ball of gas and liquid that anchors the entire system. Saturn is the second largest planet in our solar system, with a diameter of about 116,500 kilometers, roughly 9.5 times that of Earth. Despite its enormous volume, Saturn is less dense than water. If you could find an ocean large enough, Saturn would float in it. This low density reflects its composition, primarily hydrogen and helium, the same elements that make up the Sun, with smaller amounts of methane, ammonia, and water in the deeper atmosphere. The most visually striking feature of Saturn's atmosphere is the persistent hexagonal pattern at its north pole, first glimpsed by Voyager and studied in unprecedented detail by Cassini. This geometric storm is approximately 30,000 kilometers across, with each of its 6 sides longer than Earth's diameter. The hexagon is a jet stream, a river of air moving at about 320 kilometers per hour, defining the boundary of a rotating vortex centered on the North Pole. Within the hexagon, a massive hurricane-like storm spins continuously, its eye about 2,000 kilometers across, surrounded by clouds towering tens of kilometers above the surrounding atmosphere. Nothing quite like this hexagon exists anywhere else in the solar system. Saturn's south pole has a powerful vortex as well, but it is circular, not hexagonal. Scientists have worked for decades to understand why the northern jet stream takes this peculiar shape. Laboratory experiments and computer simulations suggest that the hexagon arises from the interaction of the jet stream with smaller storms at its edges. When vortices form along the boundary of the main jet, they can push and pull it into a wavy pattern. under the right conditions of wind speed and atmospheric properties. These waves appear to lock into a stable polygon. Based on the modeling, Saturn's conditions happen to favor a six-sided pattern. Slightly different conditions could produce a pentagon, octagon, or other shape. Cassini observed the hexagon through more than half a Saturnian year, watching as it transitioned from winter darkness into spring sunlight. The polar region was shrouded in darkness when Cassini arrived in 2004, requiring the spacecraft to observe it in infrared wavelengths that could sense heat emissions. As sunlight returned to the north beginning in 2009, visible light observations revealed the hexagon in stunning detail. Scientists were surprised to find that the hexagon changed color over time, shifting from blue to golden as photochemical haze production increased with the returning sunlight. High above the main hexagon, at altitudes hundreds of kilometers higher in the stratosphere, Cassini detected a second hexagonal structure, suggesting that this pattern extends to surprising heights in Saturn's atmosphere. In late 2010, Cassini had a front-row seat to one of the most powerful storms ever observed in the solar system. Giant storms erupt on Saturn roughly once every Saturnian year, about 30 Earth years, and this great white spot, as such storms are called, appeared ahead of schedule. What began as a small bright feature in December 2010 quickly grew into a raging tempest that eventually encircled the entire planet. Within months, the storm had wrapped around Saturn's northern hemisphere, its tail catching up to its head and creating turbulent interactions that persisted for the better part of a year. The storm generated the largest temperature increases ever measured in a planetary atmosphere. The stratosphere above the storm warmed by as much as 80 degrees Celsius, as energy from the deep atmosphere was transported upward. Cassini detected chemical species in the upper atmosphere that had never been observed on Saturn before, apparently dredged up from the depths by the storm's powerful convection. The storm produced enormous amounts of lightning, releasing radio bursts that Cassini detected across the electromagnetic spectrum. At its peak, the storm's cloud cover exceeded the total area of Earth. One of Saturn's enduring mysteries is how fast the planet rotates. On a rocky planet like Earth, determining the rotation rate is straightforward. You watch a surface feature and time how long it takes to complete one circuit. But Saturn has no solid surface. Its visible features are clouds that move at different speeds at different latitudes due to atmospheric winds. Scientists had hoped to determine the rotation rate by measuring Saturn's magnetic field, which should be tied to the rotation of the deep interior where it is generated. But Saturn's magnetic field is almost perfectly aligned with its rotation axis, making this method frustratingly imprecise. Cassini's measurements of radio emissions from Saturn, combined with gravity data from the final orbits, helped constrain the rotation period to about 10 hours and 33 minutes, though significant uncertainty remains. The gravitational measurements revealed that Saturn's interior is not the simple layered structure scientists had assumed. The rocky and icy core, rather than being a compact ball at the planet's center, appears to be spread out, mixed with the surrounding metallic hydrogen and helium, and extending about 60% of the way from the center to the surface. Based on the gravity data, this diffuse core could be the remnant of a more concentrated original core that has been gradually eroded and mixed over billions of years. Deep within Saturn, at pressures millions of times greater than at Earth's surface, hydrogen behaves not as a gas, but as a liquid metal, conducting electricity and generating Saturn's powerful magnetic field. This magnetic field creates a vast magnetosphere, a bubble in space where Saturn's influence dominates over the solar wind. Cassini discovered that Saturn's magnetosphere is shaped by the material ejected from Enceladus, whose geysers supply plasma that loads the magnetic field lines and causes them to rotate with the planet. The interaction between Saturn's magnetosphere and Titan's upper atmosphere creates complex electrical phenomena, with currents flowing along magnetic field lines connecting the planet and its largest moon. Part 9. Saturn's Moons, a gallery of worlds beyond Titan and Enceladus. The Saturnian system hosts a diverse menagerie of moons, each with its own character, history, and mysteries waiting to be unraveled. Cassini studied dozens of these satellites during its 13-year orbital tour, from the major moons that rival small planets in size to tiny irregular objects only a few kilometers across that were discovered by the mission itself. What emerged from this comprehensive survey was a portrait of astonishing variety, a miniature solar system in its own right, where each world told a different story about the processes that shape icy bodies in the outer solar system. Saturn currently has 274 confirmed moons, more than any other planet, though most of these are small irregular satellites, only a few kilometers across, that were discovered by ground-based telescopes in recent years. During the Cassini era, the count stood at around 60 to 80, with Cassini itself discovering 7 new moons during its orbital tour. The major moons, those with diameters greater than 400 kilometers. Number 7, Titan, Rhea, Iapetus, Dione, Tethys, Enceladus, and Mimas. Each of these worlds is distinct, shaped by different combinations of impacts, tectonics, and in some cases internal activity, and Cassini observed each in unprecedented detail. Mimas, the innermost of Saturn's major moons, bears a striking resemblance to the Death Star from the Star Wars films, a comparison that has become impossible to avoid when discussing this tiny world. The resemblance comes entirely from the enormous Herschel crater, an impact scar that dominates one hemisphere and makes Mimas look like a giant eyeball staring out into space. At 139 kilometers across, Herschel spans nearly 1/3 of the moon's 396-kilometer diameter. The crater is 10 kilometers deep, about as deep as the Mariana Trench on Earth, and in the center a mountain rises nearly 6 kilometers above the crater floor, comparable to Denali, the highest peak in North America. The impact that created Herschel came terrifyingly close to shattering Mimas entirely. Based on impact modeling, if the impactor had been slightly larger or traveling slightly faster, it would have shattered the moon into fragments that might have become a new ring around Saturn, or eventually reaccumulated into a different configuration. The fractures visible on the opposite side of Mimas from Herschel appear to be evidence of shock waves that propagated through the moon's interior, nearly tearing it apart. That Mimas survived at all is something of a miracle, a testament to the margin between catastrophic destruction and mere scarring in the violent history of the solar system. Cassini's thermal observations of Mimas revealed another peculiarity that delighted scientists and the public alike. The moon has a Pac-Man-shaped temperature pattern, with the region that receives the most direct sunlight actually being colder than the surrounding areas. This counterintuitive result appears to arise from variations in the thermal properties of the surface material. The leading explanation suggests that areas with higher thermal inertia, perhaps denser or more compacted ice, change temperature more slowly and appear cooler at noon but warmer at night. The bombardment history that created Herschel and other craters could have modified the surface in ways that created these thermal variations. Iapetus, orbiting far from Saturn near the outer edge of the regular moon system at a distance of 3.5 million kilometers, displays one of the most dramatic dichotomies of any object in the solar system. Its leading hemisphere, the side that faces forward as the moon orbits Saturn, is dark as coal, with a reflectivity of only about 4%. Its trailing hemisphere is bright as fresh snow, reflecting about 60% of the sunlight that strikes it. The contrast is so stark that Giovanni Cassini himself noticed it when he discovered the moon in 1671. He found that he could only see Iapetus when it was on the western side of Saturn, when its bright hemisphere faced Earth. When the moon moved to the eastern side, its dark hemisphere was presented, and it became invisible in his telescope. Cassini correctly deduced that Iapetus must have one side much darker than the other, and that it must be tidally locked, always keeping the same face toward Saturn. But he could only speculate about what caused this dramatic difference in brightness. For over 3 centuries, the mystery persisted. Various theories were proposed. Perhaps dark material was erupting from the interior and coating one side, or perhaps the moon was sweeping up debris from space. The Cassini spacecraft finally solved this centuries-old puzzle, revealing that the dark material is indeed debris swept up from space, but the source is more distant and the process more complex than anyone had imagined. The dark material on Iapetus's leading hemisphere comes from Phoebe, a distant outer moon that orbits Saturn in the opposite direction to Iapetus. Phoebe is dark, heavily cratered, and relatively primitive. Based on its composition and retrograde orbit, it is most likely a captured Kuiper Belt object, or centaur, that strayed too close to Saturn. Meteoroid impacts on Phoebe eject dark dust into space, and this dust drifts slowly inward toward Saturn. Because Phoebe orbits in the retrograde direction while Iapetus orbits prograde, the dust and Iapetus are on a collision course. Iapetus plows through this debris face first, darkening its leading hemisphere, while the trailing side remains pristine. NASA's Spitzer Space telescope has since discovered a vast, tenuous ring around Saturn that follows Phoebe's orbit, confirming this explanation for Iapetus's two-faced appearance. But the darkness alone is not enough to explain the extreme contrast. A thermal runaway mechanism amplifies the initial darkening. Dark material absorbs more sunlight and warms up, causing nearby water ice to sublimate. The water vapor drifts toward colder regions and refreezes there, leaving the dark areas even darker and the bright areas even brighter. Over hundreds of millions of years, this feedback process has exaggerated the initial contrast into the stark dichotomy we see today. Iapetus also boasts one of the most enigmatic features of any moon in the solar system: a ridge of mountains running along its equator for about 1,300 kilometers, rising to heights of 20 kilometers in places. These are among the tallest mountains in the solar system relative to the size of the body they stand on. If Earth had an equatorial ridge in the same proportion, it would be 200 kilometers high, more than 20 times the height of Mount Everest. The origin of this ridge remains uncertain and debated among planetary scientists. One hypothesis suggests that Iapetus once rotated much faster than it does now, perhaps completing a rotation in just hours instead of the current 79 days. A rapidly rotating Iapetus would have bulged at the equator due to centrifugal force. As tidal interactions with Saturn gradually slowed the rotation, the Moon's interior relaxed, but the surface, too cold and rigid to adjust, could have preserved the equatorial bulge as a frozen-in ridge. An alternative hypothesis proposes that Iapetus once had a ring system of its own, possibly formed by the collision of small moons or the breakup of a passing comet. This ring would have eventually fallen onto the equator, building up the ridge over time. Cassini's images of the ridge show it to be ancient and heavily cratered, indicating it formed early in the Moon's history, but the available data do not definitively distinguish between these scenarios. Rhea, the second largest Saturnian moon after Titan, is a heavily cratered ice world, approximately 1,528 kilometers in diameter. Its surface is ancient, dating back billions of years, and bears the scars of countless impacts from the early history of the solar system. Unlike Enceladus, with its dramatic geological activity, Rhea appears geologically dead today, its surface unchanged except for the slow accumulation of new craters over cosmic time. Yet even this quiet world had surprises for Cassini. In 2010, scientists announced that Cassini had detected a thin atmosphere around Rhea, composed of oxygen and carbon dioxide. This was only the second moon found to have an oxygen-containing atmosphere after Jupiter's moon, Europa. The oxygen on Rhea is not produced by life. Rather, it is created when energetic particles from Saturn's magnetosphere strike the icy surface and break apart water molecules. The oxygen atoms and molecules released by this process create a tenuous exosphere, billions of times thinner than Earth's atmosphere, but detectable by Cassini's sensitive instruments. There was briefly excitement about a possible ring system around Rhea, based on unusual signatures in Cassini's particle detectors during a flyby in 2005. If confirmed, these would have been the first rings ever discovered around a moon. Subsequent observations, however, failed to find any visual evidence of rings, and the anomalous particle detections remain unexplained, but are no longer attributed to a ring system. Dione and Tethys are similar mid-sized moons, both about 1,000 kilometers in diameter, with heavily cratered surfaces marked by bright ice cliffs and ancient geological features. Cassini found that both moons are geologically dead today, but show clear evidence of past activity, suggesting that early in their histories, internal heat drove tectonic processes that fractured and reshaped their surfaces. Tethys is dominated by two enormous features, the Odysseus crater and Ithaca chasma. Odysseus is an impact basin 450 kilometers across, covering nearly 2/5 of the moon's surface. Despite its size, the crater is relatively shallow and flat, the floor having rebounded after the impact, and nearly reached the level of the surrounding terrain. This relaxed appearance indicates that Tethys's interior was warm and ductile when the impact occurred, allowing the surface to flow and partially erase the crater's original depth. Ithaca chasma is a vast canyon system that wraps 3/4 of the way around Tethys, roughly perpendicular to the line connecting the moon's center to the Odysseus impact site. The chasma is about 100 kilometers wide and 3 kilometers deep in places, one of the largest canyon systems relative to body size in the solar system. One possibility is that it formed when Tethys's internal liquid water froze, and expanded, cracking the brittle surface. Alternatively, it could be related to the Odysseus impact, though the precise connection remains under investigation. Hyperion is perhaps the strangest-looking moon in the entire solar system, its surface resembling nothing so much as a giant sponge or a piece of irregular Swiss cheese tumbling through space. The moon is only about 270 kilometers across its longest dimension and has an extremely irregular shape, more like a potato than a sphere. Its surface is covered with deep, sharp-edged craters that give it a deeply pockmarked appearance, unlike any other world. This chaotic appearance results from a process called sublimation erosion, where dark material absorbs sunlight, warms the ice beneath it, and causes the ice to turn directly from solid to vapor. Over time, this creates a landscape of deep pits and irregular depressions. Hyperion also tumbles chaotically in its orbit, rotating unpredictably rather than keeping one face toward Saturn like most moons. Its low density suggests it is likely little more than a rubble pile, a loosely aggregated collection of ice and rock rather than a solid body. Phoebe, orbiting Saturn at a distance of 12.9 million kilometers in the opposite direction to the planet's rotation, is almost certainly a captured object, perhaps a Kuiper Belt body or centaur that strayed too close to Saturn. Cassini flew past Phoebe on its approach to Saturn in June 2004, revealing a dark, heavily cratered world about 213 kilometers across. The surface composition shows carbon dioxide, water ice, and organic compounds, different from the inner moons and consistent with an origin in the cold outer solar system. Material knocked off Phoebe by impacts has created a vast, tenuous ring around Saturn, tilted relative to the main ring system. And this is the source of the dark material coating Iapetus's leading hemisphere. Cassini also discovered 7 new moons during its orbital tour, including tiny Methone and Pallene orbiting between Mimas and Enceladus, and the minuscule moonlit Daphnis embedded in the Keeler gap within the rings. Daphnis, only about 8 kilometers across, creates beautiful wave patterns in the ring material on either side of its orbit, visible in Cassini's highest resolution images as the gravitational fingerprint of this unseen sculptor. The mission also discovered that Saturn hosts the only known examples of co-orbital moons, with pairs of small moons sharing the same orbit and periodically swapping positions in an intricate gravitational dance. Part 10, the grand finale and enduring legacy. By 2017, the Cassini spacecraft had been operating for nearly 20 years, 13 of them in orbit around Saturn. It had completed more than 290 orbits of the planet, made 127 close flybys of Titan, 23 flybys of Enceladus, and numerous passes by Saturn's other moons. It had returned more than 453,000 images and transmitted more than 635 gigabytes of scientific data back to Earth. Over 3,000 scientific papers had been published based on Cassini findings, with more being written all the time. The mission had far exceeded its original 4-year planned duration, benefiting from 2 mission extensions that allowed scientists to observe changes across nearly half of Saturn's 30-year seasonal cycle. But all things must end, and Cassini's final chapter was approaching. The spacecraft was running low on the hydrazine fuel used to point its antenna toward Earth and control its trajectory. Without fuel, mission controllers would eventually lose the ability to communicate with Cassini and to direct where it went, allowing an uncontrolled spacecraft to wander through the Saturnian system posed an unacceptable risk to planetary protection, one of the guiding principles of solar system exploration. Enceladus, with its subsurface ocean, its hydrothermal activity, and all the chemical ingredients necessary for life as we know it, could not be allowed to become contaminated by an Earth spacecraft that might carry hitchhiking microbes. Terrestrial bacteria are remarkably hardy. Some can survive the vacuum of space, the cold of the outer solar system, and years of dormancy waiting for conditions favorable to growth. If Cassini were to crash into Enceladus, any surviving microorganisms could potentially colonize the moon's ocean, making it forever impossible to determine whether any life found there was native to Enceladus or contamination from Earth. The same concern applied to Titan, with its organic-rich chemistry, its possible subsurface ocean of liquid water, and its surface lakes of hydrocarbons that might provide a different kind of environment for exotic life. After years of discussion among mission scientists, NASA headquarters, and the broader planetary science community, weighing all the options for how to end the mission, the team decided on a dramatic conclusion. Cassini would be sent plunging into Saturn itself, burning up in the planet's atmosphere like a spectacular artificial meteor. Saturn, with its crushing pressures and hellish temperatures deep in its atmosphere, offered no refuge for terrestrial microbes. The spacecraft would be thoroughly sterilized by its fiery passage through the atmosphere. But before that final plunge, there would be one last act of exploration, the grand finale, a series of daring orbits that would take Cassini to places it had never dared venture during its primary mission. The plan was audacious and unprecedented. The spacecraft would dive through the gap between Saturn and its innermost ring, a corridor only about 2,400 kilometers wide, closer to the planet than any spacecraft had ever flown. The region was unexplored. No probe had ever passed through it, and what hazards might lurk there was unknown. If the gap contained significant amounts of debris, dust, or ice particles, a collision at Cassini's velocity of more than 120,000 kilometers per hour could damage instruments or end the mission prematurely. Mission planners studied the gap using all available data, including high-resolution images of the rings and models of how particles might behave in that region. Their analysis suggested the gap was relatively clear, but there was no way to be certain until Cassini actually flew through it. The decision was made to proceed with the risky maneuver, accepting that some danger was warranted in exchange for the extraordinary science the grand finale orbits could provide. If something went wrong, at least the spacecraft would have collected valuable data on its way to an unexpected end. On April 22, 2017, Cassini made its final close flyby of Titan, number 127, using the moon's gravity to reshape its orbit one last time. This gravitational encounter bent the spacecraft's trajectory dramatically, lifting its closest approach to Saturn and aligning it with the gap between the planet and the D-ring. It was a farewell kiss from Titan, the mysterious moon that had been one of Cassini's primary targets throughout its mission. The flyby was flawless, and Cassini was on its new trajectory, committed to the grand finale. 4 days later, on April 26, 2017, Cassini completed its first dive through the ring planet gap. As the spacecraft crossed the ring plane and entered this uncharted territory, mission controllers at JPL monitored telemetry anxiously. Though with an 80-minute communication delay, they could do nothing but watch and hope. To their relief, Cassini emerged unscathed. The gap was indeed relatively clear. Whatever particles existed, they were too small and sparse to pose a threat. The spacecraft's instruments had recorded a wealth of new data about the environment in this previously unexplored region, and now it was safe to plan the remaining 21 dives. Beginning that late April and continuing through mid-September, the spacecraft performed its 22 weekly dives between Saturn and its innermost ring. Each orbit lasted about 6.5 days, with the close approach to Saturn occurring once per revolution. At closest approach, Cassini passed within approximately 3,000 kilometers of Saturn's cloud tops, closer than any spacecraft had been to the planet. During these passages, the spacecraft sampled the tenuous upper atmosphere, measured gravitational and magnetic fields with unprecedented precision, and took the closest images ever of Saturn's cloud patterns and the inner edge of the D-ring. The science return from the grand finale exceeded expectations. Cassini measured the mass of Saturn's rings by detecting the subtle gravitational tug they exerted on the spacecraft as it flew nearby. By carefully tracking Cassini's velocity using radio signals from Earth, scientists could determine how much the rings were pulling on the spacecraft and thereby calculate their total mass. The answer was surprising. The rings contain only about 40% of the mass of the Moon, Mimas, roughly 15 billion kilograms. This is far less than some earlier estimates had suggested, and the low mass carries profound implications for the ring's age. If the rings were as old as Saturn itself, roughly 4.5 billion years, they would have accumulated far more contaminating material from the steady rain of meteoroid dust that pervades the solar system. The bright, pristine water ice we see today would have been darkened by this contamination. Yet the rings remain brilliantly reflective, which strongly suggests they are relatively young, perhaps only 10 to 100 million years old. This would mean the rings formed during the age of the dinosaurs on Earth, created perhaps by the destruction of an icy moon that wandered too close to Saturn, or by a comet that was torn apart by the planet's gravity. Based on this evidence, Saturn may have spent most of its 4.5 billion year existence without its iconic rings, acquiring them only recently in cosmic terms. Cassini directly sampled material falling from the rings into Saturn's atmosphere during the grand finale orbits. The ion and neutral mass spectrometer detected a complex mixture of chemical compounds raining onto the planet from the rings above. The infalling material included water molecules, as expected given the icy composition of the rings, but also methane, ammonia, carbon monoxide, carbon dioxide, and molecular nitrogen. Most surprisingly, the spectrometer detected organic compounds, complex molecules containing carbon that must have formed in the rings or been delivered to them by impacts over time. Tiny silicate grains, probably fragments of rocky material mixed with the ring ice, were also detected. The rate of this infall was far higher than scientists had expected based on previous observations. Material is streaming from the rings into Saturn at a rate that would drain the rings entirely within a few 100 million years. This rapid loss, combined with the other evidence for ring youth, paints a picture of Saturn's rings as a temporary phenomenon, cosmically speaking. Future beings who gaze at Saturn hundreds of millions of years from now may see a planet with only faint, tenuous bands where the magnificent rings once blazed. Cassini mapped Saturn's gravitational field with unprecedented precisions during the close passes, using the Doppler shift of radio signals to measure how the planet's gravity affected the spacecraft's motion. These measurements revealed surprises about Saturn's interior structure. The planet's rocky, icy core is not the compact, dense ball that models had long predicted. Instead, the core is diffuse, extending about 60% of the way from the planet's center to its surface, and mixed with the surrounding hydrogen and helium. This fuzzy core could be the result of mixing that occurred over billions of years as convection stirred the interior and gradually dispersed the originally distinct layers. The magnetic field measurements were equally illuminating. Scientists had hoped to use the close passes to finally determine Saturn's rotation rate precisely by measuring how the magnetic field rotates with the planet's interior. But Saturn's magnetic field proved to be almost perfectly aligned with its rotation axis, to within 0.06 degrees, far more aligned than any other planet with the global magnetic field. This near-perfect alignment is puzzling. Dynamo theory suggests that some tilt should exist, and the absence of tilt makes it difficult to use the magnetic field to determine the rotation rate. Saturn's day length remains uncertain, constrained to somewhere between 10 hours and 33 minutes and 10 hours and 47 minutes, a surprisingly large range for such a basic property of the planet. The spacecraft's cameras captured extraordinary images during these final months, views of Saturn unlike any seen before. From its unprecedented vantage point inside the rings, Cassini photographed the rings as vast curved surfaces stretching overhead, their shadows falling across Saturn's cloud tops. The cameras captured the hexagonal jet stream at the North Pole from directly above, revealing details of its structure and the smaller vortices embedded within it. They imaged Saturn's cloud bands at close range, showing the boundary layers between belts and zones, the small eddies that spin off from larger storm systems, the subtle color variations that hint at composition differences in the upper atmosphere. Some of these images required long exposures, pushing the spacecraft's aging camera systems to their limits. The reaction wheels that normally stabilized the spacecraft for imaging had partially degraded over the years, requiring creative workarounds to capture steady pictures. The team worked around every limitation, maximizing every bit of science that could be wrung from the mission's final weeks. During the final 5 orbits, Cassini dipped even deeper than before, skimming through the uppermost layers of Saturn's atmosphere, rather than merely passing close to it. These atmospheric grazes, the first ever performed at Saturn, caused drag on the spacecraft that its thrusters had to counteract. With each pass, mission controllers learned more about how the spacecraft behaved in this challenging environment, gaining confidence that Cassini would survive long enough to complete its planned observations. The atmospheric samples collected during these grazes extended our knowledge of Saturn's upper atmosphere to depths never before measured directly. The 127th and final close flyby of Titan had occurred months earlier, on April 22, 2017, when Cassini passed just 979 kilometers above the moon's haze-shrouded surface. That gravity assist had set Cassini on its grand finale trajectory. Now on September 11, 2017, a final distant encounter with Titan, nicknamed the Goodbye Kiss, bent Cassini's path one last time onto an inevitable collision course with Saturn. There would be no more course corrections, no more maneuvers, no escape. The spacecraft's fate was sealed. Over the next 4 days, Cassini returned its final images. Each picture was precious, each one a farewell. The cameras captured Titan, veiled in orange haze, hiding the lakes and rivers and mountains that Cassini had revealed over 13 years. They photographed Enceladus, the tiny moon with its hidden ocean, its tiger-striped fissures, and its icy geysers that had rewritten the textbook on where to search for life. They imaged the rings in all their glory, stretching across the sky in delicate bands of ice. They took pictures of Saturn itself, the planet that had been Cassini's home, showing the bands and storms and swirling clouds that make this world so beautiful. On September 14th, at 1958 Universal Time, Cassini took its final image, a view of the location on Saturn where it would enter the atmosphere the following day. The imaging cameras were then turned off for the last time. They had captured more than 453,000 pictures over the course of the mission, from the first resolved views of Saturn during approach to this last bittersweet farewell. Their work was done. The spacecraft was reconfigured for its final mission, switching from the normal mode of recording data for later playback to a mode that transmitted continuously in real time. There would be no later. Whatever Cassini measured during its plunge would have to be sent immediately or not at all. On the morning of September 15, 2017, Cassini began its final plunge into Saturn. The spacecraft approached the planet on a trajectory that would take it into the atmosphere at a shallow angle, extending the period during which useful data could be collected. The antenna remained pointed toward Earth, transmitting at 27 kilobits per second, a thread connecting the dying spacecraft to its home planet. At about 10:31 Universal Time, Cassini entered the upper atmosphere of Saturn at an altitude of about 1,915 kilometers above the planet's 1-bar pressure level, roughly equivalent to sea level on Earth. The thrusters began firing to counteract the atmospheric drag, fighting to keep the antenna pointed toward Earth and maintain the data link. The ion and neutral mass spectrometer sampled the atmosphere, sending back data on the composition of Saturn's upper reaches at depths never before measured directly. For 91 seconds after entering the atmosphere, Cassini maintained control and continued transmitting. The mass spectrometer detected hydrogen, helium, and traces of other molecules. The data would later reveal surprising details about the atmospheric composition and dynamics. The spacecraft descended through the thickening atmosphere, the drag increasing with every passing second, the thrusters firing ever harder to maintain attitude. Then, at an altitude of about 1,500 kilometers above the cloud tops, the battle was lost. The atmospheric forces had become too strong for the thrusters to overcome. Cassini began to tumble, its antenna losing its lock on Earth. At 11:55:46 Universal Time, the signal vanished from the screens at JPL. The last photon from Cassini had left the spacecraft 83 minutes earlier. By the time mission controllers saw the signal disappear, Cassini had already been gone for more than an hour. Within seconds of losing attitude control, the spacecraft broke apart. The titanium structure that had protected Cassini's instruments for 20 years was no match for the atmospheric forces and temperatures it now faced. Components separated, heated, melted, vaporized. The radioactive plutonium that had powered the mission dispersed into Saturn's atmosphere, its heat lost in the enormity of the planet. The aluminum and titanium and silicon and gold and all the other materials that had been forged into a spacecraft on Earth became atoms scattered through an alien sky. Cassini had become part of Saturn. At the Jet Propulsion Laboratory in Pasadena, California, the mission control room fell silent as the signal flatlined. Then applause broke out mixed with tears. Scientists and engineers who had devoted decades of their lives to this mission embraced, some crying openly, others simply standing in quiet reflection. At ESA facilities in Europe and at universities and research centers around the world, where Cassini team members had gathered to watch the end, similar scenes played out. It was the end of an era, the conclusion of one of the most successful and scientifically productive missions in the history of space exploration. The legacy of Cassini-Huygens is immense and enduring. The mission fundamentally transformed our understanding of Saturn, its rings, and its moons. Before Cassini, Titan was a mysterious orange ball whose surface was completely unknown. After Cassini, Titan is a world with methane rain and hydrocarbon lakes, with sand dunes and mountains, with a nitrogen atmosphere thicker than Earth's, and chemistry that may offer clues to how life began on our own planet. Before Cassini, Enceladus was just another small icy moon. After Cassini, Enceladus is one of the most compelling places in the solar system to search for life beyond Earth, with its global subsurface ocean, its hydrothermal vents, and its geysers that spray the ingredients of life into space. Before Cassini, Saturn's rings were thought to be ancient features, formed with the planet itself 4.5 billion years ago. After Cassini, we know the rings are surprisingly young, perhaps only a few 100 million years old, and that they are gradually draining away into Saturn, perhaps destined to vanish within the next few 100 million years. The rings we see today are a temporary phenomenon, a fleeting display of cosmic beauty that happens to coincide with the brief moment when humans exist to observe it. The scientific papers produced from Cassini data number in the thousands, and analysis continues years after the mission's end. Scientists are still mining the vast data set for new discoveries, applying new analytical techniques to observations made years or even decades ago. The images and measurements are publicly archived, available to researchers around the world, ensuring that Cassini's legacy will continue to grow as new generations of scientists find new questions to ask of the data. Future missions to the outer solar system build on the foundation Cassini laid. The Europa Clipper, scheduled for launch in 2024, will investigate another ocean world, Jupiter's moon Europa, using techniques pioneered at Saturn. The Dragonfly mission, planned to reach Titan in the 2030s, will land a drone-like rotorcraft on the surface of that remarkable moon, exploring the landscapes that Cassini and Huygens revealed from orbit and from a single landing site. Other proposed missions would return to Enceladus to sample its plumes directly, searching for signs of life in the water erupting from its interior. Perhaps most importantly, Cassini demonstrated what humanity can achieve when nations work together toward a common goal of understanding our universe. The partnership between NASA, ESA, and the Italian Space Agency brought together thousands of scientists and engineers from 17 countries, speaking different languages, operating under different political systems, united by a shared passion for exploration. They built a spacecraft that operated flawlessly for nearly 2 decades, survived congressional budget threats and plutonium protests, outlasted 2 mission extensions, and returned science that will be studied for generations. In a world often divided by conflict and competition, Cassini stands as a monument to what we can accomplish together. When you look up at the night sky and find Saturn among the stars, remember what Cassini showed us. Remember that those beautiful rings may have formed relatively recently and will eventually fade away. A temporary adornment on an ancient world. Remember that tiny moons hide oceans beneath their icy shells. Oceans that may harbor life even now, billions of kilometers from the warmth of the sun. Remember that another world, wrapped in orange haze, has rain and rivers and seas, though made of substances that would be gases on Earth. Remember that we sent a piece of ourselves across more than 1 billion kilometers of space to learn these things, to see these sights, to ask these questions. The universe is vast beyond comprehension, and Saturn is merely one system among countless others scattered across the cosmos. But the Cassini mission taught us that even within our own solar system, worlds of staggering variety and unexpected possibility await exploration. Every moon, every ring, every cloud band tells a story, written in the language of physics and chemistry, waiting for us to learn to read it. The questions Cassini answered led to new questions, deeper and more wonderful than those we started with. And answering those will require new missions, new technologies, new generations of explorers. The journey of discovery never ends. Each answer is merely the beginning of a new inquiry. Thank you for joining me on this voyage through the Saturnian system, following in the path of one of humanity's greatest scientific achievements. We have traveled together from the first telescopic observations of Saturn 4 centuries ago to the final plunge of Cassini into the planet's atmosphere. We have descended through Titan's haze to land on a world of methane rain and hydrocarbon seas. We have witnessed the geysers of Enceladus erupting into space, carrying with them the chemistry of a hidden ocean. We have explored the rings in all their intricate glory, learned that they are young and temporary, and watched their material rain down onto the planet they encircle. If this exploration has inspired you, if it has stirred something within you about our place in the cosmos and our endless quest to understand, I invite you to like and subscribe to this channel. Your support helps us continue bringing you these deep dives into the mysteries of space and science. Every subscription, every like, every comment helps this channel grow and allows us to keep exploring the universe together. Until next time, keep your eyes on the stars. Keep wondering about what lies beyond the horizon of our knowledge. Remember that the universe is full of mysteries waiting to be solved, wonders waiting to be discovered, questions waiting to be asked. The Cassini mission is over, but its discoveries live on, inviting future explorers to pick up where it left off and venture even deeper into the unknown. The Saturnian system awaits our return, and when we go back, we will carry with us everything Cassini taught us, building on its legacy to reach further than ever before. Good night, and may your dreams take you among the rings of Saturn, through the methane seas of Titan, past the icy geysers of Enceladus, and out into the endless depths of space, where countless worlds await our discovery.